welcome to today's discussion. Today's discussion will mainly focus on the recursion tree method to solve the approximation of the recurrence relation from the recurrence equation and to the big O notation. So as you may know, you can solve it by the general form of master theorem. Well, that is really hard to remember because you have many restrictions and you need to fit it into the exact form of this recursion, and you need to work out which is the situation you want to use. Well, to do it intuitively, I'll introduce you a new method called the recursion tree method. Well, so first, I think all of you will be familiarized with the binary search. So let's see if we want to find 4 in a sorted list. We first eliminate the first half of the sequence and then come to the later half and really eliminate the 5 and we got 4. So it is easy to say that the recursion function for the binary search is T of n equals T of n over 2 plus 1. Well, so how can we do it? Well, let's draw a picture. So here is T of n. And as you can see, T of n equals T of n over 2. So this is n over 2, this is n, and this is n over 4, and etc. This is 1. So let's see, for each layer, we can see there is a constant 1. So here is 1, 1, 1, 1, 1, 1, 1. It's all 1, right? So how many layers do we have here? Well, as we can see, each time n will be decreased by half. So we can see n over 2 times x equals 1. Well, x, we can see x is log base to n. So here is log base to n. Well, let's see, there's a chart of here. Well, here is the number of layers. We can see it's log 2 of n. And the sum of each layer is 1. So the total operations will be 1 times log 2n, and that is log 2n. And we can see we can put the big O notation here. Well, it's really simple, right? So let's come to a slight complicated case. Well, for the merge sort, we first divide the array into half and we sort them respectively. And there is a merging stage here, and so we can see, for example, we have 1, 3, 5 and 2, 4, 6 here. Well, we want to combine them together. We first choose 1 and then we choose 2. So here we choose 3. 3 is smaller, right? And we choose 4. Okay, so the merging step would be O of n at the worst case, right? Because at the last step we need to just merge them all together, right? So here is n, all of n, right? And each time we perform the merge sort at the first half of the array and the last half of the array, and then we merge them together. So we can see it's a binary search tree here. It's a binary tree here, right? The recursion tree is binary tree. And each time for each node we have n here, and here is 2 n over 2, n over 2, and for each n over 2 we have n. Here n will become n over 2. Okay, and the sum here would be n. So the number of layer, okay, that's the same as the log base to n, and the sum of each layer is n. So as we can see, the total operation here would be n times log base to n, and we put the big O notation here. Well, it's really intuitive, right? And so let's play with it. So what if here is 1? Okay, so let's replace all of here is 1. So here 1, 1, here is 2, 4, 8. And that's a geometry sequence. So it will become something like this, and you need to have some calculations here. Well, that's really not. So here is the number of layer, right? Okay. So it will be 2 log base to n minus 1, and here it is n. So this will be 1, 2. The area would be n log 2n. Okay. Well, so for this case, a typical application is the traversal of the binary tree. Well, if we have n nodes here, then the traversal of this binary tree would have the time complexity of all of n. Thank you.